Deep within the Earth, something shifted. An invisible nudge, nearly 2,900 kilometers below our feet, briefly altered the planet's gravity. This event happened silently, decades ago, leaving behind a faint gravitational echo. For years, this secret remained buried in archived satellite data. Only now, by looking back at information from a remarkable mission, have scientists uncovered this profound event. They've found the first direct evidence of a rapid, large-scale change happening at the boundary of our planet's core, a process that unfolds not over geologic time, but on a human time scale.
This discovery hinges on the Gravity Recovery and Climate Experiment, or GRACE, a pair of satellites that chased each other around the globe from 2002 to 2017. Their mission was to track the movement of water, melting glaciers, shifting groundwater, by measuring tiny changes in the distance between them. But in doing so, they gave us an entirely new way to see inside our own planet. This ghost in the data from 2007 is now forcing us to reconsider the forces at play deep beneath the surface, forces that shape everything from the ground we stand on to the magnetic shield that protects us.
So how can we possibly weigh a tremor at the planet's core from hundreds of kilometers up in space? What could cause such a massive, invisible shift deep within the mantle? And does this silent shudder change our fundamental understanding of Earth's inner life? Let's start with where this happened. The event took place at the core mantle boundary, a vast frontier nearly 3,000 kilometers down. This isn't a simple, clean line between two layers. It's a complex, dynamic region where the solid, rocky mantle meets the swirling, liquid iron of the outer core. Temperatures here are thousands of degrees, and pressures are over 1 million times higher than at the surface. This boundary is far from static. It's a turbulent landscape of chemical reactions and intense heat transfer that influences everything happening above and below it.
The tool that spotted the change was the GRACE mission, a joint project between NASA and the German Aerospace Center. The two satellites flew in formation, about 220 kilometers apart. They didn't take pictures. Instead, they were the instrument. Using a microwave ranging system, they constantly measured the distance between each other with astonishing precision, down to 1/10 the width of a human hair. When the lead satellite passed over an area with slightly stronger gravity, like a mountain range or a large underground aquifer, it would be pulled ahead just a tiny bit, increasing the distance to the trailing satellite. By tracking these subtle changes in their separation, scientists could create monthly maps of Earth's gravity field. A team led by geophysicist Isabel Pennant was analyzing this data, looking for signals from deep within the Earth. They noticed a strange anomaly, a significant gravitational change that peaked in 2007, concentrated under the Atlantic Ocean off the coast of Africa. They first checked the usual suspects: shifts in ocean currents, groundwater, or ice. None of them fit. The signal had to be coming from somewhere much, much deeper. When surface effects were ruled out, the only place left to look was the solid Earth itself.
So, satellites designed to track water accidentally found a mass redistribution at the edge of the core. This forces a change in perspective. Instead of just looking down at the surface, we are now peering through the planet's entire mantle to witness events as they happen. For the first time, we have convincing evidence of dynamic processes at the base of the mantle that occur quickly enough to be studied in something approaching real time. The leading hypothesis for this gravity shift sounds like something from planetary alchemy. Scientists believe a mineral deep in the mantle underwent a sudden transformation. The lower mantle is primarily made of a mineral called perovskite. Under the colossal pressures and temperatures near the core mantle boundary, its atomic structure can become unstable. One model suggests that the perovskite collapsed into a denser, more compact crystal structure known as post-perovskite. Think of it like graphite turning into a diamond, the same atoms just rearranged into a tighter configuration. This phase transition would have made a vast region of rock denser, increasing its mass. That sudden weight gain deep underground is what the gray satellites likely detected. The domino effect of this change is even more remarkable. The newly densified rock would have sunk slightly, causing neighboring material to shift and creating a ripple effect that propagated down to the core mantle boundary. Researchers calculate this could have deformed the boundary itself by as much as 10 centimeters. While that seems small on a planetary scale, a sudden 10-centimeter depression in the floor of the mantle would be enough to disturb the flow of the molten iron in the outer core beneath it.
This story is strengthened by a crucial piece of corroborating evidence. Around the same time in 2007, other satellites that monitor Earth's magnetic field detected unusual disturbances, known as geomagnetic jerks, originating from the same region. The Earth's magnetic field is generated by the churning liquid iron of the outer core. A sudden change in the core's flow, prompted by that deformation of the boundary above it, could plausibly create just such a magnetic ripple. The gravitational anomaly in the magnetic disturbance, occurring at the same time and in the same place, form a powerful, cohesive picture of a single, massive geological event. Still, scientists are careful to label this as a compelling but unproven hypothesis.
This discovery fundamentally changes our perception of the deep Earth's timescale. Geologic processes in the mantle are typically thought to happen over millions of years, but this event shows that massive structural changes can occur in just a few years. The deep mantle isn't just a slow, simmering pot. It can have moments of rapid, dynamic activity. This means that future gravity missions are no longer just climate science instruments. They are now deep Earth observatories. And by understanding these rapid changes, we get a clearer picture of the engine that drives our planet's magnetic field, the shield that protects all life from harmful solar radiation. What happens now? In the short term, scientists are meticulously combing through the entire 15-year archive of GRACE data. The 2007 event is the only one of its kind found so far, but there could be other, smaller signals hidden in the noise. We may have been blind to a planet that is far more active in its depths than we ever knew.
Looking to the near future, we already have eyes back on the sky. The successor mission, GRACE Follow-On, has been in orbit since 2018, continuing the task of weighing the Earth. It's even more precise, testing new laser-based technology to measure the distance between the satellites. Now, geophysicists will be watching its data not just for melting ice sheets, but for the gravitational echoes of the next great shift in the deep mantle. We might be able to see the next one happen in real time. And in the long term, this finding must be incorporated into our models of the entire planet. If these rapid, large-scale mass shifts are a regular feature of the core mantle boundary, they could influence everything from the behavior of mantle plumes that lead to volcanic hotspots to the long-term evolution of the geodynamo that generates our magnetic field. It adds a new layer of complexity, a new beat to the slow, steady rhythm of our planet's inner life.
So, we can weigh the heart of our planet from space by tracking the delicate gravitational dance of twin satellites. That invisible nudge in 2007 was likely caused by a cascade, starting with a mineral changing its form under unimaginable pressure. And it changes our view by revealing a deep Earth that is far more dynamic and lively than we ever imagined, with processes unfolding on timescales we can observe and measure. This deep tremor is a reminder that so much of our planet's story is written by forces we cannot see, from the subtle pull of gravity to the faint light of distant stars. These invisible signals are constantly reshaping our understanding of the universe.